Hello and welcome back to Dr. Logic Awkwardly Does Logic, this time in her kitchen. It's good to see all of you again. Thank you for joining me. In this video, I'm going to do more propositional proofs because when you're learning how to do these, you can never have too many examples. I want to do this with reference to the proof strategies that I gave you in the previous video so that you can kind of see the algorithm in process. But I also want to use it as a way to illustrate some of what we will be doing in the next couple of videos, which is identifying essentially shortcuts, things that we can add to our rules that don't allow us to prove anything new, but they allow us to prove things faster. So some of the proofs that we've been doing might seem fairly long and cumbersome. We'll introduce some tricks to make them more straightforward. So let me bring up my whiteboard. There we go. And let's jump right in. So what I would like to prove is this. Ooh, not in that color. Let's go back to our nice visible green. There we go. So if it's disappearing, what is going on? There we go. If we have that U and not P implies Q, and that not O implies U, that not P implies O, and we have both. Where is it going? What is going on with my writing? Anyway, if we have not P and O, not P implies O, sorry, but we have not O and T, from all of this, we will be able to prove Q. So here's how it's set up. This is what we will be able to derive. What's the first thing that you do? The first thing that you do is you always write down all of your premises as assumptions. Every single proof starts off like this. So even if you don't have any idea how to use any of the other rules, you can always get a little bit further by writing down your assumptions. So first we're going to assume that U and not P implies Q, that not O implies U, that not P implies O, and that's both O and T. So these are all assumptions. And then, as we sometimes like to do, we will just keep a little bit of notes to ourselves of what we're trying to do. Our goal is to get the conclusion, which is Q. Now, Q is an atom. What does our strategy tell us to do when you want to prove an atom? Unless you can immediately deduce it from one of your premises through, for instance, conjunction elimination or conditional elimination, what you want to do with atoms is negation elimination. So what we will do is we will actually assume not Q, and then we'll try to show that that leads us to a contradiction, and we can therefore conclude actually it had to have been Q in the first place. So we'll start our new subproof at line 5, and we are going to assume not Q. So annotation is assumption, and then again, note to self, goal, get a contradiction, and then we will use the negation elimination rule. So what I'm writing in red are just notes to self. They're not formally a part of the proof in the way that the annotations in green are. So now we've got a bunch of interesting things. So our goal now is a contradiction. And what our strategy says is, can't help you, got to figure it out on your own, because there's no way to guarantee, there's no single way to identify what your contradiction is going to be in advance. Now, some of you might be able to see it immediately. Most of us can't, and you need to kind of work through some steps before you get to it. So can't really do anything more from the point of view of our goal. Let's go back and look at the premises. When in doubt, if you can apply elimination rules, apply elimination rules. Anytime you've got a conjunction, that is a good first step at any point if you are ever stuck, is to just apply conjunction elimination. So line 6 gets us not O through conjunction elimination of line 4, and line 7 gets us T through conjunction elimination of the same line. Now we've got a whole bunch of atoms and negations of atoms. So a good thing to do is just ask yourself, where else do these occur in our proof? So we've got Q in line 5 and also in line 1. We've got O in line 6 and in line 4 and in line 3 and in line 2. Ooh, that's very nice. And we've got T is also in line 4 and only there. Probably we aren't going to do anything more with T because essentially once we've done conditional elimination on line 4, conjunction, there isn't much more that we can do. Let's concentrate on O because that looks quite useful. In fact, not only do we have O in a variety of premises, we have not O in line 6, and that's also the antecedent of what we have in line 2. So following the rule of thumb of apply elimination rules whenever you can, we have a conditional in line 2, we have the antecedent in line 6, conditional elimination allows us to write down the consequent. So that is conditional eliminations, lines 2 and 6. Now, that's a very nice thing to have because U, what we've got here, also turns up in our initial premise. The last letter that we haven't kind of done anything with here is this P, which is in premises 1 and 3. Now, 3 also happens to have O in it, but it's a conditional. Conditional elimination requires us to have the antecedent, but we don't have not P anywhere, and it's not immediately clear how you would get it, except look at line 6 and line 3. So I'll write them over here just so that they aren't so that you can kind of look at them next to each other. So not P implies O, but we also know that O is false. Now, if a conditional has a false consequent, what does the antecedent have to be in order for the entire conditional to be true? The antecedent also has to be false. So we know that in order for both of these sentences to be true together, not P has to be false. But that's the same as not P being true. So here we're using truth tables to kind of reason our way through the premises. But if we have built our proof theory correctly, and spoiler alert, we have, anything that you can kind of get through truth reasoning, you should also be able to get through proof reasoning. So it's just a matter of figuring out how. Well, suppose that not P were in fact true. Well, if that's the case, between line 9 and line 3, we would be able to do conditional elimination to get O. So conditional elimination 3 and 9. But we already know from line 6 that we've got not O. So I'm just going to reiterate that here. And there you go. We've got a contradiction. So from the assumption that not P was the case, then you could get both O and not O. So negation introduction tells us that we can actually say, okay, if not P leads us to both O and not O, then it has to be the case that not P. So that's negation introduction 9 to 11. And would you look at that? Not P is what occurs up in line 1. It's in the antecedent of a conditional. However, we can't do conditional elimination yet because it's not the only thing in the antecedent. The antecedent is actually a conjunction. But lucky us, line 8, we already have the other conjunct. So just kind of double check your scope lines, line 13, line 12, and line 8. They're all in the same scope line, so we're not dealing with anything in subproofs or anything. So we can conjoin those two lines together. Conjunction introduction, lines 8 and 12. And of course, we did that because then we have something that matches the antecedent of the conditional in line 1. Conditional elimination gets us Q. Now, two things to notice. First of all, Q was our original goal. That's what we wanted to get right away from the very beginning. Second of all, we have a contradiction because we assumed not Q, and we were able to derive Q. So first of all, let's take care of this one. We wanted a contradiction. We have one, lines 5 and line 14. So let's use our negation elimination as planned. So we get Q, and that's negation, elimination, and it cites the entire subproof. So lines 5 to 14. However, we didn't actually need to do this step at line 5 because at no point did we use this assumption except when we finally generated this contradiction. So in fact, we could have not made this assumption and then just pretend that all the line numbers are correct. And we could have gotten exactly the outcome that we wanted, ending here at line 14. So one line shorter. Isn't that nice? Now, there's nothing wrong with the route that we did. Every single line of the proof was correct. Superfluous lines are never a problem. However, and also it's not entirely clear that you would have realized right away that you could get it this way without having to go through the negation elimination. So if this is how you would come up with a proof for this, that's fine. Perfectly legitimate proof. If, however, you are the sort of person who likes making proofs as short as possible, then you will like the fact that, in fact, this was a superfluous line, you could get rid of it, and then you would have one fewer lines in your proof. So it would actually be line 13, not line 14 or 15. Yay! If you like shorter proofs, you might also be curious about this little trick that we did here. So if you think about it, so conditional elimination says if you've got P implies Q and the antecedent P, you can get the consequent Q. What this little bit does is essentially say, well, if you've got P implies Q and not Q, then you can get not P. Wouldn't it be nice if we had a rule that allowed us to just do this directly rather than having to do this sort of little subproof? Spoiler alert again, this is exactly what we're going to look at in the next couple of videos. We're going to introduce a new type of rule called derived rules, which are essentially shortcuts, things that you will do all the time, and it gets really tedious to have to do them directly through negation introduction and negation elimination, or very tedious to do through disjunction elimination. So that's what we'll look at next time. I hope you're excited about seeing these little shortcuts. They're nifty little tricks. They make your proof shorter. But the cool thing is that whatever you prove with these new rules I'm going to introduce, you could actually have proven without. So if you don't want to learn all of them, you'll have longer proofs. They might be a little bit less straightforward, but that's okay. They're still proofs. So I look forward to seeing you all again. Take care. Cheers.